G'day, how's it going? I'm Jamie. So let's get on with this Game Boy Advance programming in C, and let's make sense of the code we've got in the GBA VS Code basic example I put up on GitHub. Let's change that, let's get it to make some more sense, and let's turn it into a little bit of a pixel plotter so we can draw some lines and boxes on the GBA. Right, let's dive into the code. Okay, so the code as it stands is pretty awful. There's a whole bunch of magic numbers throughout this code. It's not clear as to what's going on. What does writing to this hex memory address of 06000000 actually do? What is that? What's memory address 0400 0000 in hex? And what's this value of 0403? Okay, first things first, let's go through and let's define some registers for what these variables actually are and what they mean to the GBA hardware. Okay, so what we're going to do is we're going to look at this memory address here, and looking it up in GBA Tech, it tells us that it's the register for the display controller. So what we're going to do is we're going to hash define this out as reg display controller. So when we need to reference that memory address, we can use this define, so it's got a nice name. Next thing is looking at the other side of that equation, the value for hex 0403. Again, GBA Tech lets us know that a value of 3 there is for video mode 3, and a value of 400 in hex, that enables background 2. So really all we're doing here is we're telling the display controller to set video mode to 3 and enable background 2. So we'll go ahead and we'll replace this line of code with that. Okay, but first, let's go through and explain bitwise operations a little bit, because we'll be doing a lot of bitwise operations with the GBA. And you can think of a bitwise operation as just basically some sort of rule to set or turn bits on and off. Here we're doing a bitwise OR. So we're going through and we're comparing the individual bits that make up the bytes that we're operating on, and anywhere that one of these bits is turned on, it will be turned on in the result. So here we are ORing a value of 1024 in decimal or 400 in hex with a value of 3. And we end up getting the value of 403 in hex or 1027 in decimal, okay? And that's what a bitwise OR does. Anywhere a bit is turned on, or if both bits are turned on, we'll get a bit returned. Anywhere that a bit is off, we will get a 0, or both bits are off, we'll get 0. Now we'll carry out a bitwise AND with the same values. And a bitwise AND is much the same as a bitwise OR. Anywhere both bits are on, we will get a value of 1. Anywhere there is a difference or both bits are off, we will get a value of 0. So as we can see, if we AND together a value of 1024 and a value of 3, we end up with a value of 0, as none of their bits are on at the same time. Okay, so let's go through that and try this with some values we might see more often. So we'll try it with a value of 1F, which is in decimal a value of 31, okay? So it's going to have bits set from 16 on down. So bit 16, bit 8, bit 4, bit 2, and bit 1 are set. And we'll go through and we'll do this with a value of, we'll end it with a value of 4D, which is 77 in decimal. So that's going to have 0, 0, 0, 0, 0, and 64 will be on, so 32 is off. 16 will be off, 8 will be on, 4 will be on, 2 will be off, and 1 will be turned on. Now adding these together, anywhere they're both on will yield a value of 1, anywhere they're off, or either one is off, is a value of 0. So when they're the same, we get a value of 1, where they're both 0, we get a value of 0. So we end up with this value of 1101, which gives us a value of 13, or in hex notation, that's a value of D. Okay, so if you need to brush up on bitwise operators, I'll have a link to where you can look that up on Wikipedia in the bottom of this video. Let's keep moving on. So what we're going to do here is we're going to turn on video mode 3, and we're going to OR in BG enable 2. So that's going to set video mode to 3, and it's going to have the background 2 enabled. And if we run that now, you can see that line of code is a little bit cleaner, and everything still works as it did before. Okay, so looking at this next memory address that we're dereferencing, let's define that out. GBA Tech tells us this is where the screen buffer lives. So we'll define that much the same way we defined register for the display controller. We'll just call it screen buffer, and it's an unsigned short pointer, and there's the memory address. Next up, we'll define a couple of things for the GBA. We'll define screen width. It's 240 pixels wide, and the screen height, it's going to be 160 pixels high. Okay, so now we can get rid of a few of these magic numbers in the code below, and we can clean up where we're using that memory address pointer. So let's space this out, no JavaScript brackets here. And we've got, okay, so we're going through for the screen width. All right, so this is a loop going through each X pixel, and we'll go through for the screen height for each Y pixel. We'll change this to use our newly defined screen buffer variable. So screen buffer, and we'll change that 240 to a screen width. Okay, so it's a little bit clearer now that we're putting some values into the screen buffer. If we look at GBA Tech, it's going to tell us the screen buffer takes 16-bit color values. Okay, now color is a 15-bit value on the GBA with 1 bit for alpha. So in here, what we're doing is we're pushing in some values that respond to colors. So let's neaten this up. Let's put it on one line. Let's, well, if that's setting a color value, let's write a little function that takes in an RGB value and spits back out a unsigned short. Okay, we'll just call it set color, and it'll take in a unsigned char for red, 1 for green, and it'll take in 1 for blue. Okay, so as it's a 15-bit color, red lives in the lower 5 bits. So we'll just add this a value of 1F, just to make sure that 1F is, as we saw in our little Bitwise AND example earlier on, that's just the lower, that's the value of 31, so just the lower 5 bits are turned on there. So we'll make sure we don't exceed a value of 31. So we're only going to fill those 5 bits with red. We're not going to have an overflow and accidentally fill up a green value. Green, we're going to do the same thing, and it, so we'll make sure that only the 5 bits are on, and we're going to shift it up 5, so it's going to occupy 5 bits above red. And we'll do the same with blue, keep it under a value of 31, and we're going to shift it up 10 bits. So we'll have a leading alpha bit followed by 5 blue bits, 5 green bits, and then our 5 red bits at the end. And what we'll do is we'll use this function here instead of just typing the numbers out as we did. Let's call our set color function and pass these variables in. Okay, and they were in reverse order when we typed them out. You would notice that on the line 29 there, we're actually passing in blue, green, then red. So we'll flip the order we're passing these in, and we'll pass in our RGB values here. And all this operation is doing is just ANDing X and Y and adding on whatever value of T is multiplied by 5 or 3 or simply just the T value. And that gives us our quaint little color pattern that we're seeing. So remove that and we'll build and run, and we should see everything working the way it was before. Right, breakpoints hit, and here we go. Yep, it works just as it did before. Excellent. Okay, so now we've got a very simple pixel plotter. We have the screen buffer set up, and we can set individual pixel colors. The draw rate on this isn't fantastic, but this is a start. So from here, let's go through and let's start defining out a few other things. So well, the first things first, the GBA uses very specific byte sizes, and different platforms, such as we're writing this on a Windows PC right now, maybe a 64-bit platform, what is exactly the size of a float on a Windows platform versus what is the size of a float on a 32-bit platform or on a 16-bit platform. So what we'll do is we'll use stdint.h and stdbool.h just to access our sort of native types, and we'll just define them out ourselves, and we'll shorten them down a fair bit because I'm a little bit lazy when it comes to typing out unsigned char all the time. I think I'd rather just type out U8. So we'll type def uint8_t, and we'll do that for 16-bit, 32-bit, and we'll do it for our signed values. We'll just call that S8, S16, and S32. Now the next thing is we're going to do this for volatile values. Now if you've not programmed on hardware before, you might not be familiar with the volatile keyword. This is basically just saying that to the compiler not to optimize this variable out, because even though it looks like it might not change in our code at all, it may change from a hardware switch or some other interrupt that comes in and changes the value of this. So we'll mark these down as volatile variables, which means something might change this value, like if we press a button on our GBA. So, you know, if to the compiler it might say, hey, this value never changes, I could just turn this into a constant. It's going to tell the compiler not to do that. And it also lets us know when we glance at them that we expect these values to be modified by something outside of our code. So the register for display control, that's something that may get modified outside, okay, as there's other things set in there, such as the V count or the H blank, etc., which we'll go into in further lessons. We'll do the same for the screen as well, as other things may modify that. Okay, and we'll change unsigned char, we'll change that to a U8. And the same with the green and the blue variables as well. And we'll change the return value here to a U16 as well. So we can visually quite easily see what bit values are getting returned, what number of bits that we have in each sort of thing that we're playing with. We'll change T to an S32, we'll change X and Y to an S32. Even though they won't go outside the screen bounds, natively the GBA likes working with 32-bit values. It's a 32-bit processor. So to make things a little bit faster, we're going to use loop counters of 32 bits in size. All right, so let's get on with our pixel plotter. Okay, so where I can, I like to hide things away in functions so we don't have to directly call screen buffer. So what we'll do is we'll have a function for plot pixel, and it'll take an X and a Y value and a color, and it'll pump that into the screen buffer here. So the only place in our code we're going to actually be accessing screen buffer for now is inside this function. And it'll take in our Y value and multiply that by our screen width to find the appropriate row that we're on, or pixel value. And then we'll add on our X offset for whichever pixel in that row we're up to. And we'll just say that's going to equal whatever the color value is that we passed in. Now with my sort of coding style, I like to put a underscore for any variable that gets passed into a function, just depending on how long. Most of my functions are quite short, but it lets me know this is a value that's passed in, an argument. So it's quite visually easy for me to see. So for now, we've got our plot pixel function. We'll change that screen buffer down here into a call to plot pixel. We'll pass in the X and Y coordinate that we're currently at and the set color value from there. And we'll run this just to make sure everything works. Okay, there we are, loading up. And oh, breakpoint. Okay, F5 to carry on from here. And we'll make sure that we're still rendering everything as we were. Okay, yep, still rendering everything the same. Okay, so carrying on from there, we've now got a simple pixel plotter. We might as well try and use this to draw some rectangles, so fill in some filled quads on the GBA screen. To do that, we're probably going to need a left value. We'll take an upper value as well for where the top is. And we'll take a width and a height so we can fill out a rectangle. And all we're going to do here is we're going to go through a couple of for loops, starting with top value, and we'll go through and across each row as the GBA screen draws in a similar fashion to like a CRT. Even though it's in LCD, we'll just assume that it's going to draw from left to right and from top to bottom. So we'll start with Y value equaling whatever our 0 value is, and we're going to go Y is less than height. We will increment Y. And then we'll go through and we'll do the same type of for loop. We're going to go through for each X value. We'll start at 0, while X is less than our width. We'll go through and we'll do whatever's inside this loop, and we'll also increment X when we come to the end of it. Cool. So internally here, we're going to call plot pixel, and we're going to pass in X and Y coordinates. So it's going to be left plus whatever value for X we've got. We're going to pass in top plus whatever value for y we've got. And then we're going to pass in our color. Okay, so passing that in, that should let us now draw a rectangle to the screen. So let's just get rid of the code we've got here, and we'll just go through our while loop. We don't need T anymore. Okay, so we'll go through a while loop, and we're just going to draw a rectangle. And let's pass it through. Let's give it some values to draw through. So where's it going to be? Let's say we'll start at 20. We'll make it at position 20 as well. So 2020 up in the top left corner of the screen, and we'll give it the screen width minus a value of 40. Yep, and we'll do the same for the screen height. So this should fill most of the screen with a color value. And let's go through and we'll choose a nice color for this. Let's just, pass through a value of 31. So we'll have all red. We'll pass through some green, and a quarter of it will be blue. So this will probably be some sort of cyan, pinkish sort of hue. Let's see what happens if we run this. Okay, breakpoints hit, continue. There we go. We've got our rectangle drawing. So now we've got the ability to draw boxes, or filled boxes at least. Okay, stemming on from this, we should probably start drawing some lines. Now, the line algorithm I'm going to use for drawing this is Bresenham's algorithm for line drawing. And I'm going to get it so that we can draw in any sort of direction. So it doesn't just have to draw a line from left to right. We could pass through a line whose direction is from right to left, up to down, or down to up. So our values we pass in will be the X and Y coordinate for the start of the line, the X and Y coordinate for the end of the line, and the color. And if you need to see where I've pulled this algorithm from, we can have a look at, there's a link below to the Wikipedia page for Bresenham's algorithm. And it just goes through line drawing. So first off, we're going to need to get our horizontal and vertical displacement of this line. Okay, so we just get our X value and subtract our X value 1. And to get our height of the line, we just get our second Y value and subtract our first Y value. Okay, now we have sort of the displacement, width and height. Let's work out the change in the X and Y directions. Okay, so how much does this line change? And we'll go through, what we'll do is we'll go, okay, so here's a change in X, and a change in X is going to equal, so change in X dx1 is 0, dx2 will also be a value of 0. We'll have a change in Y, let's set that to 0 to start, change in Y1, and a change in Y2. Okay, so we have 4 values for change. And these values are either going to be set to plus or minus 1. So what we'll do is we'll go through and we'll say, whilst width is less than 0, we'll say that dx1 and dx2 is going to equal minus 1. We'll have an else in there, else if w value is greater than 0, we're going to have a dx1 value and a dx2 value of 1. So that's going to affect the slope of our line on X. Next we'll go through and we'll do the same for our Y value. We'll go, okay, if our H value is less than 0, then our Y1 value is going to be minus 1. And if our H value is greater than 0, then we're going to have a dy1 value of 1. Okay, now we need to figure out which is the longest side, and we'll just make an assumption about this. We'll start with assuming that the longest displacement is going to be in X, and we'll just assume that's the longest, and then we'll do a quick test to work out if we were right or wrong. So we'll go, okay, so sine 32 value, the longest is going to be W value, or the absolute value of our width. Okay, and ABS is just a function to work out, okay, if it's a negative number, we need to make it a positive number. And there is a way to do this without branching and just making use of some bitwise operations. So what we'll do is we'll go through and we'll write out a simple little absolute value function that makes use of some nice integer math. Okay, so our function is going to return a signed 32-bit integer value. And it's going to take a signed 32-bit integer value as its function argument. Now we're going to create a mask for this, so just a signed 32-bit int, and what we'll do is we'll grab our value that's passed in and we're going to shift it down 31 bits. Okay, now if it's positive, that'll shift down to 0. If it's a negative number, that's going to cause the negative shift to go down, and we'll end up with a value that's entirely filled with 1s. Then we're going to mask it with, we're going to exclusive OR our mask with that value, and then we're going to subtract our mask from it, and that's going to give us our whole number value that we started with as a positive integer. And we'll do the same thing. We did that for our longest side. We're going to do that for our shorter side, which we're assuming is our height. Okay, and then we'll do a quick test to go, if our shortest is longer than our longest side, we kind of got it wrong. So we'll test to make sure this assumption is correct. Okay, so if that's true, we need to swap these around, and that's also going to change the way that we do dx2 and dy2 increment values. So, yep, okay, we'll swap shortest and longest. We'll use a bitwise exclusive OR to do this. It stops us from adding any new variables in place. It's pretty quick to do, and well, it's just nice to know how to do this, as it's a common test on every sort of programming interview I've ever done, is if we do 3 exclusive ORs, we effectively swap the bits from the start to the other side. Okay? And now we can do a quick test. We'll just go, if h is less than 0, then we'll set our dy2 value to be -1, and else we can go through and go, actually no, if h is greater than 0, we'll make our dy value 2. Okay, if longest was the other way around, we'd never set that value, so dy2 would be set to 0 the whole time, and we'll change our dx value to 0 too. Okay, now we've come out of there. We now need to go through and let's just move this down a little bit. Okay, so we're going to go through and we're going to get half of the longest displacement. So S32, and we'll just call it numerator. And we'll grab our longest, whatever that is. That'll currently be our longest displacement. And we'll bit shift it down 1 to get half of the value. So bit shifting down something by 1 is the same as dividing by 2 or multiplying by 0.5. And we're going to go through, okay, so while a value of I equals 0, I is less than our longest side. And we'll increment I. Okay, so we're going to plot this pixel. So we'll go through and we'll plot the pixel at our X position and at our Y position, and we'll pass through the color. Now we're also, as AX, Y, and A underscore X and A underscore Y are local variables, we're going to be modifying them inside of here as well, just so we're not really creating any new variables, and we might as well reuse the ones we've got, as they weren't passed in as reference or pointers, so we can modify them, it's fine. So what we're going to do is, okay, so if that was the case, we're going to go through and we're going to increment our numerator by whatever the shortest length was. And we're just going to do a test and see if our numerator is now greater than our longest. side. We're going to go and subtract from our numerator longest. Okay, then we're going to increment our x value by whatever dx1 was, and we're going to increment our y value by whatever dxy1 was. Okay, if that's not the case, then we're going to go through and we're going to increment our x value. Oop, too many brackets. We're going to go through and we're going to increment our a underscore x value by dx2, and we're going to increment our y value by dy2. And that's our line drawing functionality. So it'll go through that for the length of the line, and it'll increment the appropriate x or y scale depending on how that longest value fares against being incremented by the numerator being incremented by the shortest value. So now if we go through, we're drawing a rect, we'll go through and we'll draw a line. We'll start at 10.5 and we'll draw it until, I don't know, 230 and 5. So we'll just draw a straight line across the top of the screen, and we'll set its color to, what are we going to pass in here? Value of 1 for red, 24 for green. So it's going to be mostly green. Okay, value of, what's that, 16. And we'll see what we get. So a turquoisey, greeny blue. Oh, there's a mistake. Okay, where have I done this? AX1. No, that should just be AX. Okay, so I'll go back up to line 62. And we can change AX1 back into AX. All right, cool. We'll build that, and it builds, no more mistakes. And now we'll get it up and running. Okay. Breakpoint, and let's go. Okay, cool. So we've got a green line across the top of the screen and a box. Great. Progress, we've now got a very simple pixel plotter. So what we can do from here is we can go through and I'll demonstrate that it can draw a rectangle somewhere else, and it's also capable of drawing lines in the other direction. So we'll draw a box that's slightly smaller in the center of the screen. We'll give it some smaller dimensions. So we'll put it at 160 and we'll just make it 40 by 40. That'll do. And we'll copy that draw line code, and we'll draw a couple of lines diagonally across the screen and maybe straight along the bottom as well. And we'll go through and do that. So now we've got a simple pixel plotter. And yeah, this video is probably slightly longer than I would have liked, but it's still just under 30 minutes. The code for this, the completed code for it's being put up on my GitHub. I'll have a link below. Starting the project, just grab the GBA basic example and roll from there. Or if you don't want to type it out as you go, you can have a look through the completed tutorials that are there. The next stage will be taking this on and sort of evolving it into a very simple version of Pong, just to get some basic movement and input happening on the GBA, and a few other small details that we'll cover. And we'll do the first half of making Pong in the next lesson after this one. Again, if you've got any feedback or comments, please comment in the video, feed them back to me. I'll address them where I can. Again, this is up on GitHub. Download it, have a play. Thanks to the comments from Reddit and on Discord last time, I fixed up the Mac version of the basic example, so it can now build and run on Mac a little bit better. It's not perfect, just due to the way that MGBA seems to work and sort of take control of the process on Mac, but you can debug on there as well. Okay, so pressing play now, I've got 4 lines in a square. So let's see how that looks. Okay, breakpoint and run it again. Okay, there we go, 4 lines in a square. All right, so thanks for tuning in and watching this. I'm gonna keep doing these because I'm enjoying it. Hopefully you're enjoying it as well. I'll try and get the next tutorial up within the week. So thanks for tuning in, and I look forward to hearing your comments. Cheers.